0.25 is 1/4.
So you have. Have the volume on this. Sorry, everybody.
Is this groovy?
Sorry, everybody. Well,
Is this groovy?
Let's try this. So we have like a 5-second delay or something. So I think fixed it, but I had to turn the volume off on my computer. So if the back and forth has gotten better, will somebody please type that in the thing? I can see. Oh, I can see it on the computer screen, not on that screen. All right, so I think we'll finish this after, okay?
Okay, that's fine.
Watching. There's 4 of you on. Hi, nice to see you all. If you, I think I have the screen set up to just show the board. If you go into the physics class, I've got a PowerPoint just with the problems that I want to do today. So that would be something to also have open so that you're not sitting there trying to see what I say. It's not working.
She said there's a lag.
There is a lag, for sure. How is the lag? What is that affecting things? How does she know that there's a lag? Yeah, but how does she know that what she's saying is 5 seconds later than what you're saying? Can I just put her on speakerphone and we can talk through this? Yeah. So I'm aware the resolution is not ideal. Is that what you're saying, Nicole?
She asked me if the yeah.
Yeah. So I planned to write big, and I wrote a bunch of things when I was testing this out, and I could read it. But yeah, I'm aware it's not ideal. But Nicole, is everything else okay? Okay, we'll do. So we've still got 4 minutes until class officially starts. So I'm just going to leave this open until then. And yeah. Okay. I'm going to do things like that. This is yours.
Yes. No, can you point to an hour 1/4? Oh. So the F is just 1 F. This is math. So it's just 1.
So what you had before was nothing has changed.
Just because I have to like know that this is one. There's nothing in there besides a one.
The things that you're not interested in.
Because if there was a 2 there, then it would be 2 divided by 8. Right?
So instead of double the force and halved the diameter.
I didn't even know that a letter is just 1 pretty much.
For the factor question, yeah, you just plug in 1 for all of the other things that you want. I need to put in 1. I need to run next to it.
Thank you. Check my notes right now.
Down to 3.
I'm forcing.
Hmm?
I'm forcing. Go. I'm still here.
All right. So, we'll officially start this. Welcome to our snow day review. I am going to only show you the board. I'm aware that the resolution isn't perfect, though I tested some things out, and I was able to read the stuff that I was writing, so I think it should get better as we go. I don't plan on showing the PowerPoint during the thing. I'm just going to focus on the board. So this PowerPoint is posted to Moodle under the exam materials, and you can pull that up to follow along with the examples. So the reason for the class, we have a test next time I see you. So the review guide is posted. There's 2 practice tests with solutions to the practice test. One of those practice tests includes some practice problems. The other one doesn't. So only one of them is only multiple choice questions. Next week we don't have lab, so there's no lab homework due, there's no lab, there's none of that stuff. And you have one final homework assignment for chapter 10. So what I wanted to do today is to go through problems that will be on exam 2. So there's 3 of them. One from chapter 7, one from chapter 9, and one from chapter 10. So the plan for today is to do some versions of these problems so that you can be well prepared for the problem solving. I don't plan on going over any of the multiple choice. The Chapter 7 question will be a conservation of momentum problem. I've listed in the review, so this is copied and pasted from the review sheet, so you can find these on the review or on this PowerPoint. I've listed a whole bunch of different problems that you have seen before that would be relevant to look at for Chapter 7. For Chapter 9, we'll do a static equilibrium problem. So this is that you'll use the sum of the torques equals 0 and the sum of the forces equals 0 to solve a problem. So I've listed 5 or 6 problems down there from Chapter 9 that you've already seen before, and we'll do an example of that today in class. And the last one will be a problem from Chapter 10, and it actually could be one of 2 problems. One will be maybe determining the pressure at various points in a liquid, and the other one will be using Archimedes' principle to determine things about buoyancy. So I've got an example of each of those that we can do in class today. Great. So if you're watching this live, I can see chat things that show up in the window. Not promising that I'll see it at exactly the moment that you ask it, but if you have any questions or something in particular is not working with the live stream, definitely let me know and we'll try to address it as best we can with any of that stuff while it's going on. So if I don't hear anything in that chat window from you, I'm going to assume that we're all good with how the technology is working for today. So I'm going to move this and stop showing the PowerPoint and just show you the screen. And again, if you want to watch PowerPoints, I definitely encourage you to get that open up and we will solve from there. So I have example 1, conservation of momentum in a collision. I have a small 100-gram cart moving at 1.2 meters per second to the east on a frictionless track when collided with a larger cart. The larger cart is 1 kilogram at rest. After the collision, the cart recoils with a speed of 0.850 meters per second. I'm looking for the magnitude and direction of the cart, the large cart after the collision. All right, so there we go. Here's my example 1 is I'm going to draw a picture before and after so that I have a better chance of seeing what's going on before and after. So my before looks like this. So I have a 1 kilogram cart that is initially at rest that is going to be collided with a smaller 0.1 kilogram cart. I'll call this one M1 and this one M2. And we're going to collide it into there. So M1 is 1.100 kilograms, and this one is 1.0 kilograms. And the speed of the initial cart is 1.20 to the east, so 1.20 meters per second. And the initial speed of cart 2 is at rest. So that's my before picture. And my after picture is gonna look, it says that after the collision, the small cart recoils at a certain speed. And we're looking for the speed of the other cart after the collision. So based on the way that this is worded, I know that these 2 carts are sticking together, because if they were sticking together and they had the same speed, then I would expect that to be part of the words. So after our collision, this cart is going to recoil with a speed of v1 prime of 0.850 meters per second. And this cart here, the bigger one, is going to recoil with a v2 prime. So that's the problem. And we want the magnitude and the direction of the large cart after its collision. Let's answer the direction straight off before we even get to anything. The direction of, actually, let's not. We'll do that at the end. So this is a momentum conservation equation. The problem that is on your test will be a momentum conservation equation. Either they will bounce off of each other, or they'll be stuck together in the beginning of the collision, or they'll be stuck together in the end of the collision. A bunch of different permutations of this type of question, but it'll be something along these lines. So the equation for momentum conservation is momentum before equals momentum after. So I'll say that m1 v1 plus m2 v2 is m1 v1 prime plus m2 v2 prime. Okay, so I'm plugging and checking now. I know both of my m's, so I've got all four of the m's in this equation covered. I know all but one of my v's. So I know that the initial speeds are 1.20 and 0 for my two carts before the collision, and I'm looking for this v2 prime. So I'll plug things in, and I have 0.100 kilograms times v1. As clear as possible, because I know that the resolution is not great on the video. I put the negative in already. Do you see it? It's going back. Yeah. So the only way that you're going to mess this up, and the main way that people mess this up when they do it, is their negatives. So the problem didn't tell me that this number was negative and this number is positive. I put that in myself. Oh my goodness. Well, apparently my computer's about to restart, which is awesome. Good to know. So I put in this negative right here. Because I knew that the cart one collided and recoiled the way that this problem was worded. So it started out going to the east and it ended up going to the west. So I decided to call east positive and west negative. And so now we'll plug in some numbers, and I have, when I solved for this, I got that v2 prime is 0.205 meters. So try and figure out where Great. So I'm going to assume that everyone else watching is okay with this. I don't have any issues. I'm going to type that in the chat window. Okay, so that is part A. It says, what's the speed of the large cart after the collision? Part B asks what the direction is of the cart after the collision. And so we know that this number here was solved to be a positive number. So I have defined in the way that I drew my equations, or the way that I drew my variables in the beginning, I defined east as being a positive number and west as being a negative number. Right? So the problem said that the cart starts out going to the east and then it recoils. So after it recoils, it'll end up going to the west, which means that v2 prime must also point to the east. I got it to be a positive number, and I've drawn things to the east as positives. So part A is that it's 0.205 meters per second. And the problem was written with 3 sig figs, so I've rounded this to 3 sig figs. And part B is that I'm going to write that this goes to the east. right. So I think that is hopefully pretty straightforward at this point. We've done a whole slew of examples of problems like this. So the hope is that this will be some easy points to get on the test, worth a little more than a typical multiple choice question would be. To go from there. Okay, next is an example from chapter 9, so a static equilibrium question. Oh, what's the question? Chat isn't working, but the video is working? Okay, what's the question?
She got 0.205. She has a mass of 0.100 on the board. Should I use that number?
Well, I really wish I hadn't just erased it. Did I label something wrong? If you've got,
I got this. Because it was 0.100 times.
we'll go back to this problem. So the mass of the small cart is 100 grams. So that mass is converted to kilograms. So the small cart mass is 0.100 kilograms. And the large cart's mass is 1.00 kilograms. And I suspect that that is an issue. Yeah? Okay. So my computer here is about to restart, which shouldn't affect the live screen, but it will. It's only going to affect the projector feed. So we won't have an example for a minute, but we still got 10 minutes. So. Okay. So for static equilibrium question, this will be a question from chapter 9 where we're using the torque sum to 0 and the forces sum to 0 to solve for different forces. And I have a figure. It says, suppose the student in the figure is 54 kilograms and the board being stood on has a 10 kilogram mass. The board is supported by 2 scales, one on the left and one on the right. Part A says, draw a force diagram that labels the locations and the direction of all the forces that are acting on the board. Part B says, what's the scale reading of the scale on the left? And part C says, what's the scale reading of the scale on the right? So let's work through this. Go back up the screen. We'll go through there. So here's our example 2, which is static.
Also, can you scroll down?
Sure. Good. Okay, so I'm going to give you a minute. Draw the force diagram as you see it, and then I'll put it up on the board. Okay, so some forces. What are the forces that are acting? There's going to be 2 weight forces acting on this board. One will be the weight of the man acting on the board, and the other one will be the weight of the center of mass of the board. And that will happen. The weight of the board will appear at the center of mass of the board. So I'll go ahead and label this whole board is 2 meters long. And so halfway between here and here will be the center of the mass of the board. So I'll put a force right here that points down. It is F, G, 1. And I think I'm going to just abbreviate that as FB in my place equations later, so I don't have to write a whole bunch of different things. And I know that that should be halfway between the centers, so I know that this distance here is 1 meter. Okay, the next thing that I want to put on here is the weight of the man, and it says that the weight of the man is 1.5 meters from here. So I'll put the weight of the man right here. I'll call that F, M. M for man, but really this is another force of gravity. This is going to be another weight force. And this distance is 1.5 meters. And those are my two forces down. This is no way that this can be a complete force diagram, because if you had a board that just had two forces pulling down on it, then the board would fall through the ground and it would continue accelerating forever. So we need some other forces to counterbalance this force that are going to point up. And those two forces are going to come from the two scales. So I have a support here and a support here, and I have a scale at both of those supports. So both of those scales are going to exert a normal force up on the board, and their force is going to point up. So I'll call this F sub N1, because this is the normal force of scale 1 on the left-hand side. And I will also have a normal force of scale 2 pushing up, which is F of N2. Okay. And I guess I should label my one last distance, which is here, which is 2.0 meters. So there's the force diagram. I have two forces that point up, and these are the two forces that the problem has asked me for. I'm looking for the weight of the board, or not the weight of the board. I'm looking for the scale reading on the left and the scale reading on the right. And I know both of these two numbers because both of these two numbers are weight forces. This will depend on the mass of the board, and that will depend on the mass of the board. Okay, so that's A. We've drawn the force diagram with the locations of the forces as indicated. For the test, I don't need you to write all of these distances, but I do want these forces to be drawn at approximately the right location and in the right direction. On the test, all of the forces will either be up and down or left and right. I won't have any forces that point in weird directions, and I won't make you combine X and Y together. So it'll either be a vertical problem or a horizontal problem. There won't be any vectors that require cosines and sines to solve. Okay, so for part B, what's the scale reading of the scale on the left? So that is FN1 that we're looking for. So it looks like that. Solving these static equilibrium problems, there's only two equations. Okay, so we have that the torques sum to 0 and we have the forces sum to 0. So let's write the forces equation. So I have two forces that point up and two that point down, and I know that the sum of the forces together must sum to 0. So sum of the forces equals 0 means that force normal 1 plus force normal 2 minus the two weight forces, so force of the weight of the board minus the force of the weight of the man equals 0. This is a hard problem to solve in the beginning because we have two unknowns in this equation. We don't know N1 or N2. So the forces equation isn't going to be a good way to start this problem, and that is usually the case. Usually your forces equation has more than one unknown in it. The next thing that we're going to look at is the torques equation. So we're going to say that the sum of the torques equals 0, and I like the equivalence version of that, which is that I can say that clockwise torques equal counterclockwise torques. And we also know that a torque is an R times an F. And if these two things are perpendicular to each other, then we don't have to worry about any angles. So I went ahead and wrote R perpendicular here. So I have a perpendicular R times an F. So Now we need to figure out a couple of things. So we're going to figure out the clockwise torques. We'll put them on the left-hand side. Figure out the counterclockwise torques. Put them on the right-hand side. And we need distances to each one of these forces in order to have torque. So we have to pick a pivot. And the choice for the pivot is something that we hope to choose in a convenient way so that it simplifies our algebra. So probably the most natural choice that people like to pick as the pivot is the thing all the way to the far left-hand side. The thing that is nice for that as the choice of the pivot is that all of these distances are to the right of our pivot, which means that we'll have only positive distances in our equation. We won't have to deal with any negatives. So I'm going to go ahead and pick that as my pivot. And that makes this location the location of x equals 0. So I have x equals 0 right here. And because I've chosen this as 0, I am 1 meter. The force of the board is 1 meter away from the pivot. So this location here is 2 meters.
So that's 0.
Yeah, so if I've chosen this to be 0, then all the way over here at the location of the normal force of scale 2, I have a location of x equals 2 meters. Right? If I'm going to
That's 0, then the other would be -1.
Okay, 1. This is 1.
If you put the force in the middle,
Oh,
then
yeah.
that'd be
Then
0.
if you put the pivot to be here, then you have a negative distance here. Negative distances are annoying, so let's just go. So I set this to be 0. So the board will have a location of x is 1 meter away from our origin. And the man will have a location which is x is 1.5 meters away from origin. So I have all of my locations labeled, my pivot chosen. I've got all of my distances, and the distances are the distances that I need. They're going to become this r in the torques equation. And now I'm ready to plug things in and figure out the torques equation. I guess the next thing that I need to do is figure out which of these torques are clockwise and which ones are counterclockwise. So if I hold my pivot here, let's see if I have a ruler. This is the location of my pivot. So I have a torque of the board, which is pulling down on the ruler. And if my pivot is right here, then I pull down on the board, and this will make this thing rotate in a clockwise direction, I believe. So both of these weight forces are exerting a clockwise torque on the board. In contrast, the normal force of scale 2 is exerting a counterclockwise torque. So I have 2 clockwise torques, 1 counterclockwise torque. And the choice of this pivot being here means that there's 0 torque from this force.
Okay, so it just cancels out.
It cancels out. So I have, if I'm looking at the torques equation, I say the torque is R times F. So this is F of N2, right? This is the force of scale 1, excuse me. This is the force of scale 1, but the R, the distance from the pivot to the location of force 1, is 0. So this is just going to be a 0 torque. So it falls out of the equation. And that's the virtue of picking the pivot at a location that you don't know anything about. So because we picked the pivot here, now there's only going to be one unknown in the equation, and it's going to be the value of this force. Otherwise, there would be 2 unknowns in the equation. Yeah, and then we have to solve a system of 2 equations with 2 unknowns, which is not something I'll ever make you do in this class. Okay. Okay, so I said I have 2 clockwise torques and 1 counterclockwise torque, so I wrote the counterclockwise on the left. So we'll say that this is going to be torque due to N2. That's my counterclockwise torque. Will equal the torque of the board plus the torque of the man. like that. And now I'm ready to plug in some distances. So torque is R times F. The distance to N2 is 2 meters. So I'll say R F N2 equals, now I should be careful, and probably the resolution isn't great here. So the distance to N2 times the force of N2 plus the distance to force B times force B plus the distance to the man, Rm, times force man. So now I've substituted torques for R's times S.
Because straight line, you don't have sign.
Yeah, so there will be no sines or cosines on the test. Everything will be all in one dimension like this. Okay, so the distance to force 2 is 2 meters. So I'll plug in 2 meters times Fn2, which I don't know, but that's a number I'm looking for, times the distance to location B, to force B, that's 1 meter, times force B. The force of B is the weight of the board. So the weight of the board is it? My computer is in the process of taking this moment to update its operating system. 10 kilograms. So it'll be 10 kilograms times 9.8 meters per second squared. So we need to get a kilogram into a weight, so we need to become newtons. Plus Rm, the distance from 0 to the location of force of the man, was that 54 kilograms? So 1.5 meters times 54 times 9.8. And I have now lost the ability to see whether or not these numbers are showing up very well. So hopefully you have it. This is 2 times F into plus 1 meter times 10 kilograms times 9.8 meters per second squared. This is torque of B plus the torque of the man plus 1.5 meters times 54 kilograms times 9.8 meters per second squared. So, as soon as I find my sheet, I'll tell you when I got
it. The left side, read the 2Tn1 times 9.8 because of gravity, but N1's gone.
So there should be no N1 on this side of the equation. Is that the question?
Yeah, should the left side read 2Tn1 times gravity.
2.
And then there's no N1.
There's no N1 because the distance to question 1.
I meant 2 and T and 2 times gravity.
Okay, so I think Nicole's question is this, which is that the question is, should I make this be mg? Right, so why am I not plugging in a g right here? And the answer to that is that this right here is not a weight force. So we plugged in m times g here because this is the force of the board is the weight of the board. It's m times g. This that we're going to solve for is going to be a number in newtons. That is the scale reading of the scale, of this scale right here. So this is going to be a number in newtons that we're not going to include as a g. So I'm just solving for what Fn2 is. I don't have to do any g's or anything like that because this force here is not a weight force. It's not m times g. It's just enough. Right? Yeah, so I'm going to round that to 2 sig figs, and I got 450. And I'll give you a minute to plug that into your calculator and make sure you get the same thing. Okay. So that is what did I just solve for? I just solved for N2. So that is what I found to be the force at this location here, which is actually what question C is asking for, not what question B is asking for. So I did C before I did B, which is fine. So now we're ready to do part B, which is what is the force of N1? What is the scale reading of the scale over here? And it'll be a number in newtons. This one. Where now I know these two, right? Both of these are just mg, where for n here I'll plug in 10, and for m here I'll plug in 4. N2 is the number I just found. I'll take the unrounded version of this number and plug it in right here. And I need to solve for N1. So now I know that F of N2 is 445.9 newtons. What is the other F? F of N1. So we don't know that yet. But we can find it from this equation right here. So I started off with this forces equation and I couldn't use it because I had 2 unknowns in it. But now this isn't an unknown. So I can plug in this number here and be done with it. So let's do that. So I have that F in 1 plus 445.9 newtons minus FB, which will be m times the mass of the board. It's 10 kilograms times 9.8 meters per second squared minus 54 kilograms times 9.8 meters per second squared. And those 4 forces all should add together to 0. And I have that F in 1 to 180 newtons. 181.3.
Fn1 plus Fn2.
Yeah, why did I do that?
Because you're finding Fn1. But you need all the forces now in the force diagram.
Yeah. So I put Fn1 plus Fn2 because Fn1 and Fn2 both point up.
So then the torques are all gone because you already used it.
The torques are gone because this was never an equation about torques. Right? We have 2 equations that we use for this. We have an equation that says that the forces sum to 0, and that's this equation. And then we have another equation that says the torques, the counterclockwise torques equal to clockwise torques. And that was this equation. So yeah, I use the torques equation first, and that's usually the case, is you use the torques equation first to solve for one of my unknown F's. Okay. And then I went up to the forces equation to solve for the other unknown F.
Oh, okay.
All right.
Would it be a negative then? Like you put the minus n on the other side?
I think if you do
Should I just multiply them all first and then get them over?
whatever order you want to do it in, doesn't matter to me. Okay, so the promise is for the static equilibrium question that forces will not be at angles. They will either all be up and down or all be left and right. You won't have to do any sines and cosines. You will probably have to use both equations both the torques equations and the forces equation. It almost always works better to start with the torques equation first, because with the torques equation, you can set the pivot somewhere at a location that makes it so that it's easy to make the torque go away. So here, the torque of N1 didn't appear in our torques equation because the distance from our pivot from the point of x equals 0 to the location of force N1 was 0. So we only had the 3 torques in the torque equation, which allowed us to solve for this third, force of N2 without having to do a system of equations. All right. So the next problem, which I'll show briefly, is a chapter 10 problem. And I know that we sort of blew through chapter 10 in class on Tuesday faster than anyone would prefer. So I actually have 3 problems I wanted to do for this, to chug through the things that are kind of difficult about this and sort of cover more permutations of different versions of this problem that could appear on the test, and also to help with some of the homework questions too. So this third example is a question about buoyancy, where I have a balloon suspended in the water, and this balloon would actually float if we let it go. So instead of it having to be held from the top, like we did for the hanging masses of metal in class, instead this balloon is tethered to the bottom. And I've given you the volume of the balloon and the density of the balloon. So the question says, draw a force diagram that shows all the forces acting on the balloon, and next it asks for the magnitude of the buoyant force on the balloon, and then finally it asks for the tension in the string. So while I get the board erased, will be a good time to start drawing the forces. Do that first part. Draw a force diagram that shows all the forces acting on the balloon. Will we have any problems involving the pressure problem in class? You mean, I assume you mean that like that you find the spot where the pressure is equal, and then you use the hydrostatic equation from there. So the question that is on the test is one of 2 questions. It is either a buoyancy question or a problem like that. So I've got examples of both of those that I want to do in class. And Brittany asked what the buoyancy is. The buoyancy is 840 kilograms per meter cubed. And the lecture PowerPoints are posted on Moodle. So if you go and open that, then you can see the PowerPoints at any point that you want. But I'll draw this diagram on the board. So here's my balloon. It's suspended in water. And the balloon has a volume, which is 75 centimeters cubed. And the density of the balloon, which I think the PowerPoint calls the density of P, because this is a plastic balloon. It's filled with plastic, not air, is 840 kilograms per meter cubed. Okay, so force diagram. We pretty much never draw a force diagram without a weight. Weight always points down. Feel free to chime in. So I'll draw the force of the weight of the balloon as Fg. And I have a buoyant force. Buoyant force always points up. So the buoyant force is going to point up. And we have tension. And instead of pointing up like it did in the problems Tuesday, and point down because the string is down. Otherwise, this is a really similar problem to what we did in class on Tuesday. So I got 3 forces, and actually the tension force and the weight force both point down, and they should just be stacked right on top of each other, but I've drawn them offset a little bit so that they're easier to see. So I got 3 forces. And the first question says, what's the magnitude of FB? So this would be a good time to check out your equation sheet and see if you can find the right equation that's going to allow you to find the magnitude of FB. Yep. So this is Archimedes' principle. You will always use Archimedes' principle, which says that the value of the buoyant force is equal to the weight of the fluid that's displaced. Okay, so the weight of fluid displaced should be the mass times G, but we don't know the mass. What we do know is that, so it'll be rho of the fluid, and it's suspended in water, so it'll be the density of the water, times the volume of fluid that's displaced, which is the entire volume of the balloon, because the balloon is totally submerged. So that'll be the volume of the balloon times G. So I've been given the density of the plastic. I haven't been given the density of water. On the back of your equation sheet, there is a table of densities if you've printed that equation sheet off in the last couple of weeks. If not, there isn't. But under the Exam 2 review materials, there is an updated version of the equation sheet that includes a table of densities. The density of water is 1,000. I think the equation sheet says that the density of water is 1 times 10 to the third.
Oh,
Yeah. So those that.
because that's in brain.
Yeah. No, I think the units of the equation sheet should be kilograms per meter cubed.
Oh yeah. She should have to.
Yeah. So that was a period, not a comma. Okay, so either one of these, this is what the equation sheet says. I wrote it as 1,000. Those are the same number. We need to figure out the volume of the balloon, but it can't be in centimeters cubed. It has to be in meters cubed. So we'll say that the volume of the balloon is 75 centimeters cubed times, and now I need to get this out of centimeters 3 times because there's 3 centimeters multiplied together. So this will be 100 centimeters in 1 meter times 100 centimeters in a meter 3 times. And I got 7.5 times 10 to the negative 5th meters. So that's not what the question asked for, but the question has asked for the buoyant force, and now we're ready to plug our numbers in. I have the density of water, I have the volume of the balloon in metric units, and G is 9.8. So FB is 1,000 times V times G and I got 0.735 newtons. The problem is written to 2 sig figs. So 75 only has 2 sig figs. So for my box answer, I'll write that FP is 0.74. But as I go on in this problem, I'll use the rounded version. So I'll stick with the 0.735 for the next step. The next question asks for the tension in the string. So I know FB, I just found it, it's 0.74 newtons. And this is the weight of the balloon. I don't necessarily know the weight of the balloon, but hopefully I might be able to find it. And I'm looking for the tension in the string. So at some point in these Archimedes principle problems, and if you're writing a note card, you want to make sure if you're totally lost, you don't know where to start, where do you start? You're pretty much always going to use this equation, and you're pretty much always going to use the sum of the forces is 0. Okay, so we're going to sum these forces to 0, and that's going to allow us to solve for the tension force. And you're going to use Archimedes' principle to find the value of the buoyant force. Sometimes you do this one first, and sometimes you do this one first. But you're always going to end up doing them both. So I'm going to erase my diagram so that I have space to do the last part. So for B, what is FT? I got 3 forces. They all sum to 0. So I'll say that the buoyant force minus the tension force minus the force of gravity equals 0. This is what I'm looking for, so I'll solve for it. So FT is FB minus FG. I'm ready to plug and chug now. In that I know the value of FB, I just found that. But I don't yet know the weight of the balloon. So usually we say that FG is mass times gravity. So we need to figure out the mass of the balloon. We haven't been told the mass of the balloon. We have been told some other things of the balloon, and I just erased them. We were told its density and its volume, right? So I have the density of the balloon is 840 kilograms per meter cubed. And the volume of the balloon, 7.5 times 10 to the negative 5. If only there was a way to find the mass given the volume and the density. Yep, there sure is. Yep. So I have the density is mass over volume. So mass must be density times volume. By the way, this is where the formula from Archimedes' principle comes from. Right? The buoyant force, Archimedes' principle says the buoyant force is equal to the weight of the fluid displaced. The weight of the fluid displaced is the mass of fluid. And the mass of fluid is density times volume. So that's where this equation comes from. This is just that the buoyant force is m times g, where these two numbers here, the v and the rho, are going to tell you what the mass of the fluid is. So the weight of the balloon is going to be the density of the balloon times the volume of the balloon times g. Is the mass. So then you need to multiply that times gravity. And I got that is 0.01176 newtons. Oh, I'm ahead of myself. Yeah, I gave you the answer to the tension of the string. So this is 0.063 times 9.8. you said that number is what?
0.6174.
So this is 0.6174. This is 0.735. This number here. Now we're just going to subtract them. So the tension in the string is FB 0.735 minus FG 0.6174. All right, what's the question?
It's frozen and it's all black.
Frozen and all black. If anyone else is listening and has that problem, can you let me know? Is it back up now? I'm trying to decide if the problem is on my end or on your end. So if you are listening and you hear something, will you type just a word in the chat window so that I can see if anybody else is here?
So you can hear stuff, but you can't see it.
Cool.
Now it's all good.
Everything is all good now? So I know that Alina and Brittany are somewhere here. So if you're here, could you type something in the chat screen? Tell me if you're having the same problem. We had somebody, Nicole says that the screen went black for her for a while. So just to recap what we did, I said that the tension force, I used Newton's first law to say that these three forces have to sum to 0. These two forces point down, so they both went in as negative numbers in Newton's first law. And I solved for the tension force, the difference between the buoyancy force and the weight of the balloon. I had to find the value of the buoyancy force, which I had just found in the previous step. So I just copied that over. I also had to find the weight of the balloon. I didn't know the mass of the balloon, that wasn't told to me, but I did know the density and the volume of the balloon. So I used the density and the volume to give me the mass, and I got that weight was 0.6174, and I subtracted them and found this to be the tension in the string. I sure do. So before I put a box around something, I'm always going to check my numbers are significant digits. So that is 0.00.12. All right. Okay, so there's a buoyancy force question. I want to do one more buoyancy force question. So I'll put it up. And this is about something that is not sinking. So every buoyancy problem we've done in class so far has been a buoyancy problem for something that's not floating on the top of the water. But now let's do one for when things are floating on top of the water. So I have a block of wood floating in equilibrium at the surface of a tank of water. The block of wood is a 10 centimeter cube, and it has a density of 700 kilograms per meter squared. And there's three parts again. I'm going to draw the force diagram that shows all the directions of all the forces acting on the block of the wood, just like I did for the previous problem. And then part B says what's the volume of water that's displaced by the block of the wood. And part C is what is the distance from the top of the block to the water if this is fresh water. So it has the same volume that we are dealing with there. So while I get the board erased, if you can start drawing this on a piece of paper and work on the force diagram. Okay. So here's my block of wood in the water. Wood block here. I don't know sort of what portion of it is above the water level and what portion of it is below the water level. I draw the water level. It's a straight line, so it's more clear. So I'll just sort of draw it looking something like that. And first thing that I need is a force diagram. So these things always have at least two forces. We have the weight of the block. There's always a weight force. There's always a force of gravity. And then we also will always have the buoyant force. So this is going to look like we have the force of gravity, the weight of the block, and then I have the buoyant force, which points up. And those two things always, buoyant force always points up, the weight of the block always points down. And now the question is, are there more forces? Nope, there's not. I don't have a string, there's no string. The only other thing that can sometimes show up on a force diagram for something suspended in liquid is if something is sitting on the bottom. If this was sitting on the bottom, I have the buoyant force that points up. I have the weight force that points down. And there would be friction. Friction is only there if it's moving. So there's no friction because nothing is moving. We have the normal force.
Oh.
Okay.
The point.
So I would have a normal force that points up if something was sitting on the bottom of this tank, because it's resting on the bottom of the tank. But we're not at the bottom of the tank. Maybe. I haven't totally set what your problem is going to be for the test. So it's in the realm. It's in the realm of possibility for things that could be on the test. Okay, so I have two forces, and what do I know about the magnitude of these two forces? These two forces can't be different. They have to be equal and opposite from each other, because this is a block that's resting in a liquid. It's in equilibrium, which means that these two forces have to sum to zero, so they have to cancel each other out. So once I know some things, I can go. Okay, I'll write down the only other thing that it told me, which is that the block are 10 centimeters. It's 10 centimeters cubed, so it was 10.0 by 10.0 by 10.0 centimeters. And I also know that the density of the block is 700 kilograms per meter cubed. And then I'll also write down the density of water, since it's suspended in water. And that's 1,000. Okay, so I've done A. I've drawn a force diagram that shows the directions of all the forces acting on the block of wood. And now the next question is, what's the volume of water displaced by this block of wood? So how are we going to do that? So there's two things that you will do in every one of these buoyancy questions. Newton's first law is one of them. The other one is write down the formula for the Archimedes principle formula for the buoyancy force. So I'm going to write both of them down and we'll try to decide which one seems like the best path to go. So Archimedes principle says that the value of the buoyant force is equal to the weight of the fluid displaced by the object. So this is rho of the fluid. So rho of the fluid is water, so density of water, times the volume displaced, times G. The other thing that we can look at is Newton's first law, which says that these two forces have to sum to zero. So I will say that FB minus FG equals 0. Okay, so I have two different paths here, and I think I probably need to use both of them to answer this question. Right, here is what I'm looking for. Right, we're looking for the volume displaced. So that's what I'm looking for. I know the density of the water. I know G. I don't know FB.
So you find the mass of the graphene.
Yeah. So I can find FB from this equation. As soon as I know the weight of the block of wood, I can solve these equations because I know that those two numbers will be equal and opposite. Once I find the buoyant sweep force, I'll plug it in here and solve for the volume displaced. So that's the procedure. So we just need to figure out the weight of the block. I sure didn't. It's going to be the mass of the block times G. I didn't give you the mass of the block. But I did give you the density of the block and the volume of the block. So it's the same thing as last time. So we need to figure out the mass of the block. That will be the density of the block times the volume of the block times G. The biggest way people mess these things up is by putting in the wrong row and the wrong V. So I got two different rows here. I have row that's the density of water, and I have row that's the density of the block, right? Archimedes' principal formula always includes the density of the fluid. So this one always goes here. The weight of the block better depend on the density of the block and not the density of water. So I'm going to plug in the density of the block here. Same thing with volume. Archimedes' principle says that the buoyant force equals the weight of the fluid that's displaced. So I need the volume of fluid that's displaced in this equation. But when I go down here and I'm trying to figure out the weight of the block, well, the weight of the block depends on the entire volume of the block, not just the volume of the block that's underneath the water. That's the trickiest part about these things, is which row goes where and which V goes where. You have to think about it every time. So I think with that there, I've got all of these numbers. I should figure out the volume of the block though. So from the dimensions of the block, I'll go down here and say the volume of the block. I could do this in centimeters and then divide it by 100 times. Oh, sorry, I didn't realize you couldn't see that portion of the screen. Okay, so I wrote over here the dimensions of the block being 10 by 10 by 10. That means that the volume of the block is going to be 10 times 10 times 10, but that would give me centimeters cubed. And then I'd have to convert that. So I'm just going to convert them to start off with. 10 centimeters. I moved the decimal place 2 places to the left to get that to meters. So that'll be 0.1 meters. So I'll just do 0.1 meters and 0.1 meters and 0.1 meters. Because this is a cube, the volume of a cube is its length times its width times its height. So those three numbers multiplied together give you the volume of the block. And that is 0.001 meters cubed. So now I'm ready to plug those numbers in here. And I'll do the density of the block. And I got 6.86 for that. That's the weight of the block. Okay. Does that work for you? Is that what you got? Okay, great. Okay, so the weight of the block is 6.86 newtons, which means that the value of the buoyant force is also 6.86 newtons. So if I solve this for FB, I'll get that FB equals FG, which also equals 6.86. Now I've got this number, which is my buoyant force, and I'm ready to plug that in up here. Here's the value of the buoyant force. I know the density of water. I know G, and I don't know the volume displaced. That's what the question is asking for, so I'm ready to solve for it. So I will say that the volume of the displaced fluid, we'll solve for this, so I'll divide both sides by rho G. That'll be FB divided by the volume of water. So I said I'm going to divide both sides of the equation by rho times G. So if I divide by rho times G here, then all that's left is the V. And if I divide by rho times G here, then I have
So even though that's in the middle, I can keep it around.
because these are all multiplied. So this is one term right here. There's no pluses or minuses anymore. So you can do that.
Okay.
And now I'm plugging my numbers. So this is 6.86 divided by 1,000. And I got 7 times 10 to the negative 4 meters. Although I want to do this in 3 sig figs because all my things were written in 3 sig figs. So that is 7.00 and negative 4 volume. So if I Oh, so Brittany said, can I explain how I did centimeters to 0.001 meters? And that is obviously a centimeter. I did that 10 centimeters. Right, this block is 10 centimeter cubed. So 10 centimeters is 0.1 meter. So I said that the volume of the block will be the length of the block times the width of the block times the height of the block. And so rather than doing that, that's 10 centimeters times 10 centimeters times 10 centimeters, and then having to convert centimeters cubed to meters cubed when I'm all done there, I just converted these to meters in the beginning. So instead of putting 10 centimeters here, I put 0.1 meters here because 10 centimeters is 0.1 meters. So it's not that this is 0.001 meters, it's 0.001 meters cubed because it's the 3 dimensions all in meters multiplied together. Okay. So for C, what is the distance from the top of the block to the water if this is fresh water? So here is water block. And to be honest, if this was on the test, this would probably be the bonus question on the test. This is a harder question. So here is my block of wood. And here's my water. And the question is asking for what is this distance right here? Okay, so what's the distance from the water, top of the water to the top of this block? It's 10 centimeters total in height. How tall is this? How far is it above the water? Not going to be half. There's the formula for the volume of the block, right? So the total volume of the block is this number that was 0.001 because we multiplied them all together. The volume of the water that's displaced by the block is the volume of the block that's below the water. Does that make sense? Say that again. The volume of the water that's displaced by the block, that's this that we solved for. Right? This number here is the volume of water displaced by the block that we needed for Archimedes' principle. Is 7 times 10 to the negative 4 meters cubed. That's equivalent to the volume of the block that's under the water. So if we displaced this much, then this much of the block is under the water. Okay? So I could say that 7 negative 4, that's the volume that's under the water, equals the length of the block. Well, that's still 10, right? The whole length of the block is underneath water. So that'll still be 0.1 meters times the width of the block. That's also still 10, because the whole width of the block is underneath the water. Times the height of the block. Where now the height of the block that's underwater will not be 10, it will be some number less than 10 that I can solve for. So let's solve for it. I have 7 10 to the negative 4th divided by 0.1 twice. And I can say that H is so the height of the block that is below water is 7 centimeters, 0.07 meters. The whole block is 10 centimeters tall, and 7 centimeters of it is below water. So how much of it is above water? Right, so the whole thing is 10 centimeters tall, or 0.1 meters tall. 0.07 meters, or 7 centimeters of it is below water, and that leaves 0.03 meters, or 3 centimeters to be above. I'm going to write that as 3 sig figs. 3 sig figs, I'd write it as 0.0300 meters, or you could write it as 3.00 centimeters. Fun problem. Definitely a bonus problem. What a fun bonus problem. Okay. All right, so buoyancy problems. We figure out the value of the buoyant force. We have 2 equations that we always use. We use the buoyancy force equation from Archimedes' principle, and we use Newton's first law. Some combination of those, plus maybe a little bit of thinking, will get you to the end. All right, I have one last problem, which will hopefully not take too long. And I think this is the question that Alina had. Is this the sort of question that will be on the test? So the answer is either there will be a buoyancy problem or a question like this is the problem-solving question. But I promise not to waste your time, so I will put an easier version as a multiple choice question of one of these. So they'll both be on the test, just only one will be a long problem-solving question. All right, so I've got a tube filled with mercury. So in this section of the tube, I have mercury. One end is exposed to the atmosphere, so here's atmospheric pressure right down here. And the other end is connected to a reservoir filled with gas. So I have gas the other end of the tube. And the question says, what's the pressure of the gas at the interface between the gas and the mercury? So what is the pressure right here in the tube? So I'm going to get the board erased and start drawing the diagram on the board. The steps when you solve these problems is that we always do two things. We figure out where is there atmospheric pressure, or where is there a pressure that we know. Usually the pressure that we know is atmospheric pressure. And then we want to find a spot where we can draw a line that is helpful, where we can find two spots that are at the same elevation where the pressure is equal. So think about that while I get this up in the board.
Between the two, there's nothing. There's nothing. There's nothing on the other side.
What other side here? This is all air. So the pressure here is the pressure of the atmosphere. Are the slides not up on Moodle? I think that they are up on Moodle. So I think the slides for this are up on Moodle. The slides don't have solutions, but if you go to the exam 2 review materials, it should be the very top link on the exam 2 materials for the slides. Okay, so here is my diagram where I've said that I've got mercury filling up most of the tube. I've got air in this section of the tube, and I guess I'll draw some dots here, or whatever this is, and it has some pressure of heat gas. That's what I'm looking for. The other thing that the question lists is that it says that the pressure over here is exposed to atmospheric pressure, and it says that P of the atmosphere is 101,300 pascals. And I've been given some distances, so I was told that this distance from the top of the mercury to the bottom is 6 centimeters on this side.
You want to give us the atmospheric pressure?
I would never expect you to memorize that. I realized after I posted it that this number isn't written on your equation sheet, and I think I will just tell it to you for any problem that you need. I wouldn't expect, no numbers would ever be something I'd expect you to memorize for this class. I think even G is written on an equation sheet. If you could possibly make it to this part in the semester without having to memorize that number, it is on the equation sheet.
Okay.
And then I was told that this distance here from the top of the mercury on the left-hand side to the bottom is 16 centimeters. So I will draw that there. Okay, so the two things we are looking for is where is the pressure, atmospheric pressure, and where can we draw a horizontal line that will be helpful? Because the pressure along any horizontal line, as long as we are looking in a connected fluid, will be constant. So for me, the first question is the easier one. Right here is atmospheric pressure. Everywhere, atmospheric pressure doesn't vary a lot with height. So the pressure here is atmospheric pressure all the way down to the pressure here is atmospheric pressure. Because air is a gas, its density doesn't vary on the scale of anything other than like kilometers. So on just a few centimeters distance, it'll still be 101,000. So I'll have P is the atmospheric pressure, which is 101,300. And now where can I draw a straight line? I want to draw a straight line through a connected fluid. So drawing a straight line from here to here doesn't work because I have gas over here and mercury over here. I want to draw a horizontal line where I can find that the pressure is the same. Right? So the pressure along this horizontal line is the same pressure. Pressure at depth of the fluid is a constant. Pressure at this horizontal line is also along that line the same pressure. The most appealing place to draw a straight line that would be helpful for this problem So I know that the pressure right here is atmospheric pressure. So that means that the pressure over here at the same height better also be atmospheric pressure. Those two spots are at the same pressure. So I will say that the P right here is also 101,000. Okay, so now I think I've gotten all of the tricky things that I can get from the test, and the equation that you're going to use for this problem will always be the hydrostatic equation. So the version of it that is written on your equation sheet is P naught plus rho G delta H. Is that it says P is P naught plus rho G delta H. So the pressure in some fluid is the pressure, a reference pressure plus the density times G times the depth of the fluid, delta H. Now we need to figure out what numbers get plugged in where. This is the hardest part of this question. Yeah, we'll have to change the millimeters. Yeah, for sure. So I guess the real question is which one of these? So we're going to be looking on this column, right? And we're looking for this pressure right here. That's what the pressure asks for. It says what's the pressure at the interface between the two, between the liquid and the gas. So this is the pressure that we were looking for, and this is the pressure that we know. As you go down in a fluid, the pressure always goes up, right? So the deeper we go in this fluid, the farther you go down in the pool. This is the reading this question that everybody missed. The deeper you go down the pool, the higher this pressure is. So whatever this pressure is here, it better be a number that is less than this. So I'm going to use that to help me figure out which one of these two numbers is 101,000. Well, if I plugged in this, then I'm going to add the density times the height, and I'm going to get a number bigger than 101,000. So you're right. Usually, this is atmospheric pressure. But the reason is because usually atmospheric pressure is our reference pressure. But actually, right now, we're looking for the height here at the top of the fluid. Yeah. So the way that I'm going to write this is that I'm going to say that pressure of the gas, right? The pressure at the top of the fluid plus the pressure due to the weight of this column of mercury is going to equal this 101,300. Plus the tricky part in this question. Right, so I know that this number has to be the biggest number. So if the way that you plug these things in ends up that you end up getting an answer that's bigger than this up higher in the fluid, then you put the wrong number in the wrong P in the wrong spot. So at the top of the fluid, we have the pressure of the gas, and as we go down this depth, delta H, we end up with a pressure at the bottom, or at this reference pressure right